but I'm going to say everything I just said. So we are going to do this practice problem. I've changed the presentation to be hopefully shorter and more clear based on previous years. If you watch this, who cares? This question requires you to use this equation. The delta S naught equals the sum of the products minus the sum of the reactants, where N and M are their coefficients. Okay, sorry about that. Resume the recording for once in my career. All right, so this is a product, this is a product, these are the reactants, correct? So it's the sum of products minus sum of reactants, and we have to make sure we include their coefficients. So I'm going to take 1 times PBI2, correct? So the sum of 1 times 175 plus 2, right, of KNO3, that's 150. You with me so far? Okay, and then I'm going to subtract. I'm going to move it down here because I'm ugly. Well, I'm not ugly. Okay, so I'm depressed now too. With 250 plus 2 times, what was that number? KI 125. Is that right? Did I bring all those down right? That was kind of annoying how I did that. And you end up with, I don't know, what'd you end up with? Negative 25, okay. So you'd end up with A. Fair enough. Really? Okay. I tried to choose the ugliest one, but there wasn't a color of Tom. I'm just joking. I actually look fire today, so I know I'm good looking. Don't even worry about it. Okay, could you do that on a test? Okay, good. Next. Well, there's the answer. So there it is. Yep. Okay. Here's the next one. These extremely commonly, these are just thinking problems. Like A, predict the sign of delta S, and then justify it. That's an extremely common. So you have sodium solid plus chlorine gas goes to 2 sodium chloride solid. And it tells you delta H is negative 410. That means it is what? Exothermic. All right, it gives heat out. All right, okay, here we go. A, predict the sign of delta S for this reaction. Justify your answer. Delta S is not related to delta H. Delta G is related to both S and H, but S has nothing to do with it separately. So how do we answer this one? We don't need to look at the table. You can look, like you can, I should say yes, you could, Tim. Or you look that it goes from 3 things, and some of them were a gas, to 2 things which are a solid. That is a decrease in entropy, which is a negative sign. Negative because we have a decrease in the number of gas molecules and a total decrease in free moving molecules. You okay with that? Like, I feel like yesterday we were okay with that one, like we covered. So far, both review things we've done. All right, now actually calculate it. Okay, so it's the same thing we just did. You want to do it, or just want to see the answer? All right, I heard do it, so we'll do. There we go. All right, so delta S will be negative. A gaseous reactant is converted to solid product. If you ever decrease the amount of gas, entropy is going to decrease. Gases are the most random, highest entropy substance, and we got rid of it. All right, and then part B would have been negative 181.1. Raise your hands if you got that right. Okay, if you need help on how we got that, It's right here. You can come back and watch the video later. Okay, that's not what I wanted it to do. Okay. Okay, this is just a summary. So if you've been watching these AP videos, it introduces it, gives you practice, and gives you the summary. So in summary, entropy changes can be found by taking these from tables. You have the sum of the products minus the sum of the reactants. Next, the sign of entropy change can be predicted from the states of reactants and products. All right, here are the things. We wrote them yesterday in a different way, but we wrote these similar. Entropy is positive if solid goes to a liquid, to a gas, or negative if a gas goes to a liquid or a solid. So the state change, hopefully you remember that from yesterday. If the number of moles increase from reactants to products, especially the state change going to a gas is involved. So are we okay with these so far? Okay. That was from yesterday. We talked about that. Okay, this is the Gibbs free energy, which is where we got to yesterday. And then, I don't know, I didn't feel like it was my greatest teaching moment ever, or probably your greatest learning moment ever. And it's pretty important. So let's make sure that we get through it together. So chemical reactions proceed until equilibrium is reached. We know that. I hope by now we do. All right. Some favor the reactants and some favor the products. And we know that from K, but this K's coming back in a minute. But for now, we don't know. So we use this idea of Gibbs free energy. Gibbs free energy change, or delta G, describes whether a reaction is thermodynamically favorable or unfavorable, which means if it's favorable, it goes to okay, it happens naturally. Sorry, like without us putting energy in. That's spontaneous. And then common misconception, just because a reaction is favorable doesn't mean that it happens quick. That's really important that you don't tie the two of them together. It could happen without outside energy, but that doesn't mean it happens instantaneously or fast. It could be a super slow process. Right, it's going to rust, but it takes a very long time. Good. All right, so what is delta G useful for? Once again, it's useful to tell us at the current conditions of whatever we have, is the reaction going to proceed spontaneously or non-spontaneously. So Gibbs free energy change for a chemical process in which all reactants and products are present in standard state is given as delta G naught. Now, standard state, I sort of talked about it yesterday, but here we go. They're pure substances, meaning we know not a mixture. All right, it's 1 molar solutions. It's a gas at 1 atm. All right, those are the standard conditions. It didn't give the temperature, but it's at room temperature. If we have delta G naught, it means it's standard conditions. Goddard's doing his sound day, so we'll get annoyed a few times. Luckily for me, I'm going deaf. So like that one thing where he measures going from low to high, I check out real early. It's kind of scary that I'm going deaf. All right. So here we go. Now, we can't just be given a G and then go, oh, hey, delta G is this. We can't. It's like saying we know it's 70, but what was the change of temperature to get here? Well, we need to know other stuff to know that. You okay with that? We can't just say, oh, it warmed up or it cooled down. We don't have enough information to know that. All right. Then one more thing. Even if Gibbs free energy is less than 0 under some conditions, that does not imply that delta G is negative and vice versa. Don't stress about that part. Here we go. So the standard Gibbs free energy change for a physical or chemical process may also determine from the standard, Gibbs free energy of formation of the reactants and products. So this should look exactly the same as delta S and delta H did, and as we did yesterday. All right, this presenter loves greater than and less than signs. which I don't. I would rather just say the word negative or positive. And so whatever, like if you don't care either way, it doesn't matter. But if delta G is negative for a process, it's thermodynamically favored, which is a long way of saying it's spontaneous or it happens without us putting in outside energy. Okay. We will find delta G two different ways. This is the less confusing way, like in my opinion, and then we'll learn the second one. Okay, are we good with this? So this is a really important part, is just to know what the sign of delta G naught means. If it's negative, it's going to happen. If it's positive, the reverse is going to happen. If it's at zero, any guesses? Did we already say it yesterday? It's an equilibrium. So yeah, they're going both ways at the same rate, so there's really no net change. Okay, here we go. This is going to combine them both. And this is a thought question from the multiple choice. The decomposition of hydrogen peroxide is represented by the equation above. Now, looking at the equation above, there's some important things here. We have something aqueous going to a liquid and a gas. So that's going to be important. And then we have that it is what type of reaction? Exothermic. All right, so here we go. A student monitored the decomposition of that, yada, yada, and recorded the concentrations as a function of time. In this particular problem, this is useless information. Where would that be, though? Where have we seen this before? This is a rate law. So if this was really on the AP test, this might be a question. And then there'd be like another one. Is it first or second order? And you just plug this in and take the ln of list one, right? Or L2 versus L1 and then L1 over. Right. Yeah. So that would not be in this section. But if you see a table like that, then that's what you would do with that. It has nothing to do with this particular problem, though. Okay. So the reaction is thermodynamically favored. I highlighted that. This is actually telling you something about G. What does it mean? Negative. All right, so this is a fancy way of saying G is negative. So I can get rid of this one. There's a D, whoops, which would be the other one that says G is negative. I promise. I didn't realize I cut that without getting all the way. So these two would be gone, right? And then delta S, and I know I don't have D on there, but this is the right answer. How do we know delta S is positive? All right, because we went from one, well, two technically, but I mean one thing into two separate, and we definitely increased the gas. That's the most important. We went from no gas present to gas present. You okay with that? All right, so delta G is negative and delta S is positive. Okay, so who knows what H2O2 is? Hydrogen peroxide. And we store it in what? I have it right here, actually, by chance. I was wiping up some blood earlier today. What kind of bottle? A really dark, opaque bottle. And that's because this reaction happens on its own pretty slowly, but even light will cause this reaction to speed up, and you just end up with bubbles, right? Like not real fast. If you put in Ki, then we end up with the elephant toothpaste that we did. But this reaction does happen on its own for those reasons. We never did? What a loser. Okay, I'm not going to do it right now because it'll take me 10 minutes to set up, but I promise if you will remind me, like during some B time, I'll have it all ready. But you got to remind me on a B time so I have it ready. Okay, moving on. So delta G is negative, the equation, yada, yada, yada. We good with that? Are we okay, 100% okay with when entropy increases? You're going to be asked that 3 or 4 times. It could be from math. It could be from just analyzing qualitatively. Okay, here we go. The hydrate of that can be heated. What if you read a question and you're like, I don't know what it means by a hydrate and anhydrous? Should you skip it? No, it doesn't matter. Okay, hydrate means it has water like stuck to it. That's what that dot means. In my potassium iodide, this stuff is really annoying to store. It also comes in a black bottle. I buy this as a powder, but if you listen, it mostly sounds empty, and that's because it absorbs water from the air. That's why this cap is in there, and then it just kind of sticks together as a solid. It's really annoying because I have to like stab the crap out of it. See there, like I dug into it right there. Okay, so some compounds attract water and bond to it to be more stable. Like, right, it wouldn't necessarily be like a compound in like an ionic or any type of bond. It's just more stable that way. So that's what it means by a hydrate. It's hydrated. What do you think anhydrous means then? Not water. So we literally just drove the water off. Okay, we typically do that by heating things. Okay, moving on. Can be heated to form anhydrous salt. Yada yada. Use the data in the table below. Calculate delta G for this reaction. So what would we do here? Okay, yep. Sum of products minus sum of reactants. I want to pause for a second and make sure and point something out. This is extremely important. This is like level 9 out of 10 importance. You see this unit. What is the top of this unit? These are in kilojoules. So this is a delta G value, and delta S values are in joules, and that can ruin your life. Okay. All right. S is in joules. So that's kind of weird, right? But when we're going to eventually use both of them in an equation, you have to make sure that you convert both of them to the same one. It doesn't matter which one. On the test, you could say 1200 joules or 1.2 kilojoules, and you'll get it right either way. But they have to be converted to the same. That's in your future. Okay, here we go. Back to this table. We'll go pretty quick. Give me that as quick as you can. So let's move to the next. It should have the answer on it. All right, so we get 18.22 kilojoules. You what? Yeah. Yep, per mole. This, anytime you see a negative on a unit, it means it's under. So it's kilojoules per mole. The negative is just putting something, the negative exponent puts it in the denominator. If you got it wrong, do you know where you went wrong?
Yes.
Okay. All right, summary here. And really for Gibbs, this is like half of it. And then there's the more confusing half coming up. The Gibbs free energy change for a chemical process in which all the reactants or products are present in standard states gives the delta G naught. The standard Gibbs free energy change for a chemical or physical process is measured with that. If G is negative for a process, it is said to be thermodynamically favored, which means it's spontaneous or it's going to happen without outside intervention. Okay. All right. Thermodynamically favored. So we have this combination of H and S now that we're going to talk about. So it is sometimes necessary to consider both enthalpy and entropy to determine if a process will be thermodynamically favored. So these problems, you're not going to have a data table that gives you the G naught values. You're going to have to do more work. All right, if enthalpy and entropy values can be predicted or determined at a given temperature, then the standard Gibbs free energy change can be calculated directly. All right, so this is what we have here. Delta G is equal to the enthalpy, which will either be given to you in the problem, or you have to take the sum of products and the sum of reactants for delta H. And those are going to be in kilojoules. Then you have the temperature in Kelvin. And that is multiplied by delta S, which is in joules. And delta S can either be calculated out of a table or will be given to you in the problem. Or sometimes it doesn't ask for a specific answer. It just asks you to reason knowing that S is either a positive or a negative value. You with me? Okay, this to me, and I could be way wrong to all of you, this is where it gets confusing, is this term. Because this sign is sometimes negative and this sign is sometimes positive. You with me? Now, delta H can be negative or positive as well, but we're not subtracting something that may be a negative or a positive. So it gets really weird. If this is a negative, you're really adding. If this is a positive, you're really subtracting. Okay, welcome to two negatives, or negative positive or positive negative. All right, so I've changed these to plus and minuses. If you like the greater than less than sign, sorry, talk to my 4th grade teacher. Maybe she didn't teach it to me very well. I still get annoyed. Like I know the alligator eats the bigger number, but just a random sign without two numbers there, I'm like, okay, anyway, moving on. In general, the temperature conditions necessary for a process to be thermodynamically favored, or when G is negative, can be predicted from the signs of delta H and delta S. So a little bit complicated table here. If delta H is negative and delta S is positive, these are the two combined. It means it's spontaneous at all temperatures. Because no matter what you do, you'd end up with a negative number, because you're starting with a negative number and you're going to you're going to subtract a positive value, and that will always stay negative. Did I make it in the final cut? No, I walked away too soon. Fine, I'm not voting for Seth. Just kidding. I won't say who I'm voting for. Like, I mean, obviously I'll vote for my child. That's the only thing I'm going to divulge. Yep. Oh no, no, it's incriminating. Okay, if this is the reverse, where delta H is positive and you subtract something that ends up negative, that means you're going to add, right? So they will always be a positive value in that combination. It will never be spontaneous. So what it really means is the reverse is spontaneous at all temperatures. Okay, then those aren't too tricky. It gets in here. Now it matters, because the temperature, it may or may not be spontaneous at one or the other. So this is where it gets tricky. If it's positive and positive, you have a positive value that's being subtracted, because remember, it's minus T delta S. So we have delta H, and in this instance, we're saying it's, oh, those are some slippery clothes, apparently. We're saying this is a positive. The answer here will be positive as long as that is smaller than that, right? Which means this temperature, if it's small, then we're going to be fine. So if it gets high, though, that's when we get the negative value. And so when we have the positive, it's spontaneous at high temperatures, because this term has to exceed that term. All right, and then negative, negative, that's only at low temperatures. Because you're going to have now, I don't know, I'm saying the word positive and negative so many times, our minds are going to explode. We have a negative number minus a minus, which means you're really going to be adding, right? And so now we need to keep the T term low in order to get something spontaneous. Okay, if that clicked in your head, you're due for a 40 on the ACT. Yeah. This takes a lot of reasoning, and this is what I would do. If you have time and you don't know the answer, just put in 2 different temperatures and see what happens, because the math will do it. The math will also do this if you're stuck. All right. So this is just saying what I just said, actually. So in cases where both enthalpy and entropy are favorable, no calculation of delta G is necessary. You don't have to do the math here because it will always be favored. Or it will always or will always not be. So this is saying this top row and the bottom. Sorry, this is poorly colored. I don't know if I could make this fatter, but we'll try. So it's saying, whatever, the top 2 rows, we don't have to do math. We can tell, oh, hey, that will always or it will never be. The bottom 2 are where we have to do calculations. Okay. So here we have some questions. Now, there's not actually a question on there, is there? No, there is. Okay, no, there isn't. So this is the stem. These are your 4 options. Okay, so here we go. The elements K and Cl react and yada, yada. Refer to the information above in the table below to answer the question that follows. This is another one. This has, like, this is just confusing as all get out. That would be probably for a follow-up question, but we don't need to know whether what these values are for this specific question. Okay, we know that this is exothermic. All right, we know delta H is a negative value. You with me? All right, what else do we know about S? Tell your partner, not me. What do you know about S by looking at that? S is a what? It's a negative. There is a decrease in entropy. Go ahead.
Why can't they do stoichiometry right?
They did it right, didn't they?
Oh, never mind. I'm lying.
Remember, I warned you that you'd get fractions on these because it's supposed to be in 1. So that's why they have the half right here. And it's screwy. Who wants a fraction in your reaction? Oh, what other word can I run? I don't know, but or we end up with subtraction, traction. Michael Jackson. I am for real. Oh no. Okay. It's observed that it goes to completion. Like, oh wait, that worked. Right. Which of the following is a true statement about the thermodynamically favorability of the reaction? Okay. So it says it happens. And here, well, one more time. We knew delta H was a negative. Okay. Which that means like it wants to give out energy. That means it wants to happen based just on energy. But remember, it's a balance between energy and entropy, right? You with me? And then this one is a what? This is a negative in entropy. It's a decrease in entropy. Does that happen naturally? No, it does not. Okay, here you go. So which of these statements is true? It goes to completion. So which one of these is true? Okay, tell your partner what your guess is. Or what you know the answer is. Any ideas? Okay. All right. Anyone confident enough to tell me what they think the answer is? You thought it was B. Thank you for being confident. Anyone else? B. Lots of B's. D. An E. Okay, the answer is A. Oh, all of a sudden everyone's happy. I didn't hear one single person say A. Okay, my bad. Okay, here we go. It is A for the following reasons. None of you got it right. Well, 3 of you got it right. It's A. It is favorable because of what information in the problem? No. What? Because it goes to completion. Now, it does that, but that's not the reason why we know it's favored. It happened. Like it literally did its job and went to completion. That means it's favored. It's going to happen, but not because of entropy. That said, it shouldn't have happened, right? The enthalpy, the THAL, that says it should have happened. So since it was favored because it went to completion, it could only have happened that way because the enthalpy change drove it in that direction. Kind of okay on that one? It's a tricky question, but I don't have another one like that. I'll find one, but not this minute. Okay, so you gotta, it's a tricky one to just find. Go ahead.
How are we gonna know what it's under? Or it's like
Yeah, they'd have to say something about how it stayed as solid or something like that. Like it would have to give you that information. All right. You can read that if you want that. I think that's pretty similar to what I said. Okay, Preston, is this what you were thinking? Like that answer? You said you thought it was A, your justification in your head. Okay, Brooklyn, kind of. All right, Corbin, yes or no? All right, well, this was a pretty concise explanation. All right, so this is where it kind of like all comes together. And if you can do this problem, you're in a good spot. All right. So this is being the free response section. It has this big nasty looking reaction up here, which is not really that big a deal. We put silver in really concentrated acid. It shouldn't really react, but if we highly concentrate it, we get this reaction to happen. All right. So I want to pause it and give you a little while. We don't have it. Okay. For this one, just for speed wise, I'm just going to go to the answer for each one. So the sign, the entropy change is positive. Do we all have an agreement on that? Like we can knock that one out of the park in 3 weeks. All right, because the reaction has 1 mole of gas in the products and none of the reactants. If we ever increase the moles of gas, we've definitely increased it. Okay, and when they do the AP practice ones, they'll give you the scoring guidelines as well. To get 1 total point, you have to do both on this one. Okay, 43 kilojoules per mole. Who had that? Raise your hands. Well, that says it's 43. So we have all that plugged in. Okay, I can't hear it already. Glorious. It's gone. I can't even hear my daughter talk anymore. Just kidding. I can. So one more time, 43. Raise your hands if you have 43 right. All right. Letter C, probably the hardest part. Would we agree there? The reaction is more likely favored at 95. Who had that right? Okay, we went lower there. All right. At higher temperatures, the T delta S is larger. So the term we're going to subtract. All right. And positive, which means if we subtract a positive, we're getting closer to a negative number, more negative. What's that? Right, because we're going to subtract it. If it's positive, we want a big T to make this more exothermic. We kind of arrive with that one. That's the trickiest one. But when in doubt, again, plug it in. And it would tell you like, oh, hey, I got a negative 80 and a negative 92. Oh, apparently the 95 or whatever. I made those numbers up. I don't know, whatever. Okay. And finally, like you got to love these questions. AP will give you an easy one once in a while. So how do you separate it? Well, this gas is already gone, right? Unless you did it in an enclosed vessel, and it doesn't say that if I remember. All right, so all you got to do is let the water evaporate by distillation, boiling, or letting it just evaporate, let it dry, anything like that, you would be fine. Okay. Who feels better today than yesterday? Okay, good. All right, in summary, in some cases, it's necessary to consider both enthalpy and entropy. Knowing the values of those works out. In general, the temperature conditions necessary for a process to be thermodynamically favored can be predicted from the signs of delta H and delta S naught. There's only one last section of this chapter. We'll cover that tomorrow. Well, I cut out a ton of stuff. Okay, never mind. There's two. Sorry, there's two sections, but they're not bad. Oh, I need to end this.